The topic in today's lecture is deoxidation of steel. So, I have studied steel making, then we have talked about little bit about the tapping operation, and I have indicated during my last lecture that during the tapping itself, the first deoxidation of steel is going to be carried out where the bulk reduction of dissolved oxygen content will be taken up. Okay? And this is not the final the end of deoxidation. Deoxidation is carried out in several stages, but this is bulk of the deoxidation is going to be carried out in the ladle during the tapping itself, whereby we can bring down oxygen from 600 level to about 50 or 100 ppm, and then the final adjustment can be done at a subsequent stage. So, deoxidizers are those elements which are added into the steel. So, this shows a scenario, depicts a scenario where molten metal is being filled or tapped from a furnace. It is almost nearly filled, the ladle. So, we have a freeboard height which is available here, and then the gas stirring is also going on simultaneously, because the moment this stream is exhausted, we require some amount of stirring in the system, and it is the gas stirring. So, argon is non-reactive, it produces, its job is only to create stirring. We will see the mechanism of gas liquid coupling, study the mechanism of gas liquid coupling later on, but let us concentrate on deoxidation, that how the oxygen is reduced from 600 ppm to about 100 ppm. So, if you look at the guidelines for addition of deoxidizer elements can be obtained from the Ellingham diagram, where we see which elements has increased activity or capability to react with oxygen. And if you, so those lines which are lower in the Ellingham diagram, which essentially indicates that the resultant oxides are extremely stable, those are the elements actually which we will be looking at in order to take away the heat, take away the dissolved oxygen. In that context, if you look at just on this particular, concentrating on this issue, that we require deoxidizers which should, which have a lower position in the Ellingham diagram, metal oxide line X and XO line. X is any species, XO line essentially I would say XM, because the oxides could be Al2O3, FeO, Fe2O3, M and N could be different from oxide to oxide. So, if the metal and the oxide, metal oxide line is lower in the Ellingham diagram, that element is suitable for us for deoxidizer, but that is only the one requirement. Okay? And in that list, therefore, if you look at, we will have aluminum, silicon, calcium, sodium, etc. appears to be extremely high, the preferable candidates for deoxidation. Now, even magnesium, okay. But we will, there are several other categories, for example, considerations, the behavior of the deoxidizer elements. It is not only their affinity towards oxygen, all the species which I have listed here could be, from, theoretically speaking, are a correct choice of deoxidation, because they have great affinity towards oxygen, they will be able to reduce oxygen from the bath itself. But the price is another consideration, the hazards of adding the deoxidation, because deoxidizers are going to be at room temperature, okay, and you have to add that deoxidizer into liquid steel at 1600 degree centigrade. For example, material like sodium, etc., will vaporize in no time, for example, and as a result of which their efficiency, they can be hazardous, and of course, most of the sodium you have added will be lost from the system, they will not dissolve into steel because of high vapor pressures, low boiling point. What is going to happen, bulk of the sodium will be lost from the system without taking part in the deoxidation process itself. So, merely affinity of oxygen is not, affinity towards oxygen is not the single criteria, the price is an important parameter, the hazards of addition, their recovery, etc., are important consideration and looked at from such standpoint, okay, we find that all these conditions are very nicely satisfied by two candidate deoxidizers, and these are principally aluminum and silicon. They have reasonably good what do you call affinity towards oxygen. Silicon has relatively poor in comparison to aluminum, but nonetheless it has quite good affinity towards oxygen. The price is moderate, their addition is less hazardous, the recoveries are often quite good. So, we will not use these as deoxidizers despite the fact that they have great affinity towards oxygen. So, therefore, elements like aluminum and silicon etc. are going to be added into the tapping stream, because these are going to be added in the solid. So, how does it go? It goes like aluminum as solid, and then aluminum becomes liquid, and then aluminum becomes dissolved. This is the state in which the reactions proceed, and then once aluminum dissolves, then the aluminum will react with dissolved oxygen and form Al2O3. That is the reaction is going to proceed. Solid aluminum, perhaps because it is 600 ppm oxygen. So, solid aluminum will have virtually no scope to see a dissolved oxygen, but the moment both oxygen and aluminum are in the dissolved space, in the dissolved state, and that there is a good amount of stirring, there is a good possibility that oxygen and aluminum will come into contact with each other and then form alumina, which is of course. We must understand that this is the deoxidizer element, this is the dissolved species, this is the deoxidation product, and in this particular case the deoxidation product is a solid product, and therefore, two species dissolved which you cannot see, all on a sudden they react together and then form something which is. So, there is formation of a new phase like Al2O3 will be preceded, chemical reaction will take place, but really we can see that Al2O3 has formed will depend will proceed via nucleation as well as growth. So, not only aluminum critical nuclei has to be there, critical nuclei has to grow, and then only we will have a bigger particle of Al2O3. Okay. So, nucleation and growth is a characteristics of the deoxidation process, because we form altogether new phases. Silicon, for example, while aluminum is going to be added in pure aluminum form, commercial aluminum, silicon is never added as pure silicon. Okay. Silicon is added as ferrosilicon. You again have high carbon ferrosilicon, low carbon ferrosilicon. Okay. You have to be very careful while adding, because they can, and this comes out with lot of impurities also. It can have, depending on how crude the process of manufacturing of ferrosilicon is concerned, a significant amount of impurity. So, now you are moving towards purer and purer steel. You can see, pig iron had lot of impurities, crude steel making has got lesser impurities, and now you are going to go to secondary steel making or ladle metallurgy, subsequent processing operation or the downstream operation, that will improve the purity, and you cannot afford to add an impure material like ferrosilicon, which will bring in lot of impurities and jeopardize the final quality of steel. So, you have to carefully, even parts per million level will make lot of difference, as we can see later on. Particularly, for example, I would say the calcium content in ferrosilicon, you can note down that this statement, quote unquote, calcium content of ferrosilicon it influences the efficacy of calcium addition, which we will study later on, half a lecture or so, in steel making operation. So, you have to have adequate purity of ferrosilicon. We also have deoxidizers like silicomanganese. This is also a popular deoxidizer. Okay. Now, deoxidation product, when you use ferrosilicon or silicomanganese, for example, the deoxidation product could be liquid. You have deoxidation product which could be gaseous. If you use carbon, hypothetically speaking, then the deoxidation product is carbon and oxygen reacting, forming carbon monoxide, which is gaseous. It will not contaminate the steel, okay, because the gas bubble forms, gas bubble escapes from the systems without contaminating metal. But if it is liquid, like if you have silicon, then you form silico-manganese in certain ratios 45:55. If you can form silica manganese silicate, having wet percentage 55:45, then you can get a liquid silico-manganese manganese silicate, and so you can have a deoxidation product, okay, not solid as it is in the case of aluminum, so which is alumina. It could be liquid also, but no matter, because carbon is not a candidate for us. We want to deal with steel which does not contain much carbon. Carbon is driven out. So these candidates essentially show us that the deoxidation process will always produce a new deoxidation product. Okay. Now, when you add deoxidizer elements, these deoxidizer elements melts and then dissolves, and therefore the reaction can take place anywhere here. Okay. So the deoxidation product can be generated anywhere in the system because of the circulatory nature, molten steel containing dissolved aluminum and dissolved oxygen reacting, and thereby forming the nucleation and growth can take place on this wall. It is a heterogeneous reaction, here also, on the bubble surface also, everywhere multiple sites are possible for nucleation of these new products. The solid and these products, okay, are basically oxides. So their characteristics are, whether be it Al2O3 or be it manganese silicate, we will have these products contaminating steel if they remain in steel. So the deoxidation products are essentially lighter than steel. Okay. Their densities, they are oxides, so they are substantially lighter. So they have a natural tendency to float up, and if you hold the ladle for some amount of time, okay, the cleaning action starts, whereby all the deoxidation products which have nucleated here, they can grow as a function of time and then gradually float up and join the slag metal interface, or go to the slag metal interface to be absorbed by the overlying slag phase itself. So if you have a liquid slag, if you can engineer the slag properly, in that case the slag should be able to absorb manganese silicate as well as Al2O3 particles, which will be continuously rising through the melt itself. Having given you this background, okay, and preliminary the preliminary aspect of deoxidation addition during the tapping operation, let us look at the thermodynamics of the deoxidation reaction. Al dissolved by L. So the first part we understand is the melting and dissolution, and the melting and dissolution is a heat and mass transfer phenomena. Melting is a heat transfer phenomena, dissolution in steel is a mass transfer phenomena, and these are going to be aided by convection. So they are going to be pretty rapid in this particular system because of the large difference in temperature, and because the steel does not contain already a large amount of silicon, etc. Okay. So therefore the driving force for mass transfer, or the gradient of concentration and gradient of temperature are enormous, and because you have a good amount of stirring, so as a result of which the moment, and these are low melting point constituents relative to steel. Okay. Silicon of course does not melt in aluminum melts in steel, it has a melting point of close to I think 800 degrees centigrade. So the melting is very rapid, and dissolution too is not slow. So the aluminum is available in the dissolved state, and so is silicon, and then the reaction takes place, Al2O3, the solid products form, and nucleation growth is as I have indicated. So we will say 2 aluminum and 3 oxygen, and we can write K equilibrium constant if there is a equilibrium means what? If there is, if the oxide product has nucleated here, okay, if this is the oxide product, so the melt and the oxide product, there is an equilibrium, that is what we are talking. So there could be melt, oxide as well as slag equilibrium also, but we are not talking of that. We are, because this has nucleated within the melt, so therefore we are talking about equilibrium between the melt and the deoxidation product. That is what, if this equilibrium is established, then we have activity of Al2O3, and then we have activity, and we can say that this is Henryan activity of aluminum squared, and then Henryan activity of oxygen cubed. That is what it is. K equilibrium, we all know, is given in terms of, which is related to the standard free energy of formation of the oxides. K equilibrium is given in terms of equations like for oxidation reactions, this is the standard formula in which A and B are constants. If you take for example 1600 degree centigrade, then for log K aluminum, K equilibrium for aluminum Al2O3, it comes out close to I think 17. On the other hand, if you take similar reactions for I would say silicon and oxygen, okay, silica solid, not manganese silicate anymore. So, it is silicon dissolved plus oxygen dissolved, and that is why the product, and here what we are going to see, this product is going to be 4.62 or something like that, log K equilibrium silicon 17 point something, I think 32 or exactly, marginal variations could be there. What does this indicate? That, so these are with respect to pure, this oxide is a pure phase, so the activity is equal to 1, okay, and therefore you can understand that you will have this term is going to be extremely large, for example 17.13, which essentially indicates that this term is going to be, the product of the two terms are going to be extremely small. Okay. Now, larger is this particular term, more product is going to be smaller. So, therefore, if you compare this, the two deoxidizers for example, and for the same level of oxygen, you can immediately understand that the H aluminum value is going to be for a given level of fixed oxygen level, and that the deoxidation products have pure solid state as the standard state, that means their activity is equal to 1, we can look at this equation, look at the value of K equilibrium, and then conclude that for the same level of dissolved oxygen, okay, the residual, the aluminum content, the activity of aluminum in the melt, this is what the third bracket indicates, that aluminum is now going into the melt, okay, and you are replacing oxygen. This is a tragedy of the steel making process. I mean, you try to drive out one element and the second element gets into it, but the question is that by choosing appropriate elements, we can drive out more than we put in, and that is what happens basically with aluminum deoxidation. So, for the same level of oxygen activity in the melt, okay, we can, if you compare the two scenarios, we will find that the dissolved equilibrium dissolved aluminum content in the bath is going to be much smaller than silicon. So, therefore, I will say that aluminum is a more powerful deoxidizer, and this assertion comes out or follows readily from the Ellingham diagram itself, because aluminum diagram is lower than the silica diagram. So, aluminum, then comes silicon, then comes manganese. This is the order of the strength of the deoxidizers. So, if you want to get 10 ppm oxygen for example in Mn with manganese, the manganese wet percentage concentration in steel could be about 10 wet percentage, but on the other hand, if you get 10 ppm oxygen with aluminum, the aluminum content on steel could be about only 400 ppm, and this is because of the simple fact that aluminum is a far more powerful, and this follows from the equations that I have written here. Now, it is also true, from here you can see that if you can typically this activity is equal to 1, it is in the pure state, but suppose if you have MnO also forming, that both the elements you have added simultaneously through silico-manganese as I have indicated, okay. So, some oxygen will be reacting with manganese, some will be reacting with silicon, and then you have adjusted the composition of silico-manganese in such a way that both these react together to form a liquid deoxidation product. We will see that why liquid deoxidation product is advantageous for us a little later, okay. Then you can conclude that the activity of silica is no more going to be 1, it is going to be significantly less than 1, because the simple fact that manganese oxide and silicon dioxide are in combined state. So, silica is fixed, so therefore, the activity coefficient is going to be smaller. So, now I can make another conclusion based on this thermodynamic observation, that if I use two elements which have opposite nature and they can react for deoxidation and they can react with each other to reduce their activity, okay, it is possible to get the same level of oxygen by using lesser level or having lesser level of contamination of the molten metal. So, suppose that is why I say if I use silicon, ferrosilicon alone as opposed to silicomanganese, and my target oxygen in both this case is suppose 200 ppm. Okay. So, I can say that it is possible if you find that the silicon content of the bath in this particular case is suppose 0.6 wet percentage. I am arbitrarily quoting the value, okay, and in this particular case it will come out, the silicon content is going to come out to be 0.4 wet percentage or so, because the equation is chemical reaction is shifted towards the right, because it is a tendency now that if you eliminate SiO2, okay, that is what is happening when you have manganese oxide there, which is reacting with eating up silicon dioxide. So, this is a predominant more preferential, the forward arrow or the forward direction is the more preferential direction of the reaction. In that case what happens, the efficiency of deoxidation reaction really increases. So, the contamination or the residual silicon content as a result of deoxidation, when Al2O3 product has formed, some aluminum has gone into steel, and this aluminum is the residual aluminum due to deoxidation. So, therefore, even though we have eliminated, I have been saying this during my lectures, even though we have eliminated all of silicon during primary steel making process, because of deoxidation, because of residual silicon content coming from the deoxidizer elements, we can see that the final steel will contain some amount of silicon. Of course, that level of silicon has to be within the maximum value specified by my customer. Okay. So, I will use all deoxidation elements in such proportions such that the prescribed target composition, the target composition is not violated at all. So, I have a choice, I have various deoxidizer elements available, ferrosilicon, silicomanganese, aluminum, and I will do that in proportions, okay, such that I have little bit of aluminum content, I have little bit of residual silicon content, but not too much silicon, aluminum or manganese content, that they are over and above the one or the ones which are prescribed by the customer itself. When you use one single element, aluminum by far is the most powerful. If you want to produce an ultra low oxygen steel like 10 ppm or so, you have no option but to use a deoxidizer like aluminum. On the other hand, if you want to have 50 ppm oxygen or 100 ppm oxygen, okay, possibly silicomanganese deoxidation, silicon deoxidation is good enough for you. So, for very low low carbon steel, I would say if you want to have carbon also low and oxygen also low, because normally carbon, if carbon is low, then oxygen tends to be higher, but I am saying that you have lower carbon and lower oxygen. So, it is low, we say that LCAK, low carbon aluminum killed steel. So, there you have to do killing, killing means the carbon oxygen reaction, or there is not much residual oxygen left in the system, that is what is the meaning of a steel is killed, when we will say that it contains virtually no oxygen, free oxygen or dissolved oxygen in it. So, therefore, in such cases you have no option but to use aluminum as the most powerful deoxidizer. But if you are using silicon as a deoxidizer element where your requirements are 100 to 200 ppm of dissolved oxygen, in that case perhaps it is better to use, because target oxygen is fixed, you have fixed it at 100. You have option now, you can either use ferrosilicon, you can use ferromanganese, you can use silicomanganese, and I am saying that I would like to use silicomanganese in such cases, because if I use silicomanganese, because the simple fact that the activity of silica and MnO are going to be reduced, and because I will be moving towards a lower residual content of the deoxidizer element in the metal, and that is in steel. So, I will prefer silicomanganese as opposed to the silicon, because I will get to the same level of oxygen no matter I use manganese or I use silicomanganese or I use ferrosilicon. But if I use ferromanganese alone, then the manganese content of steel is going to be very, very large. If I use silicon again, it is going to be intermediate, and if I use silicomanganese, in that case the silicon and manganese content are going to be very, very small. And this kind of deoxidation where we have two elements added together, and this is by far the most common such deoxidizer. We call them as complex deoxidizer, or the resultant deoxidation as complex deoxidation. So, when one element will be added like aluminum, good enough, it is alone powerful enough to drive the oxygen. Okay? So, we will say that we have added aluminum to remove oxygen, we will call that as simple deoxidation. Two or more elements, you can engineer your deoxidation process, simple deoxidation and complex deoxidation. So, thermodynamically these reactions are feasible. There is absolutely no problem. There is a standard free energy reduction is there from reactant to product. So, as a result of which we can say that we have we could reduce the oxygen level itself. Now, if you see where is the aluminum that we have added has gone, let us explain with respect to let us not talk of different deoxidizers, one by one is good enough, or if I cite examples with respect to one, it is going to be enough. But I think before I address that point, so I will like to add that silicon with oxygen, this is the complex deoxidation reaction. So, that is we have SiO2, and then we have Mn also reacting with oxygen forming MnO, and then MnO and SiO2 combining together forming MnO plus SiO2, okay, and that is forming manganese silicate. Not always, provided they are in certain proportions. So, 45 mole in terms of molarity or mole ratios, there is a 1:1 mole roughly if they come and combine with, if you use a ferrosilicon, for example silicomanganese, where you have 70% Si and 30%, then you may not get a liquid deoxidation product itself. So, the composition of silicomanganese is adjusted in such a way, nearly 1:1 proportion, nearly 1:1 proportion, such that you can look at the manganese silicate phase diagram, for example, MnO-SiO2 phase diagram, and you can find out that where are liquid phases originate. So, you may have a range of compositions where you can have deoxidation and yet have liquid products. I have not categorically mentioned the advantages of liquid and solid products or disadvantages, that is going to be discussed a little later. Okay. So, the aluminum that we have added into steel, where it is gone? So, the aluminum as per the reaction has manifested in the dissolved aluminum in steel, one part, and the second part is that aluminum is sitting there with oxygen as Al2O3. Okay. So, some oxides, if we sum them up, so this is the total alumina that has formed, and then we have the metal where we have everywhere, if you say homogeneous, we have dissolved aluminum. So, if you do aluminum balance, how much of aluminum we have added, you find out that how much of aluminum is in the dissolved state by spectroscopic analysis, how much of Al2O3 has formed, if you can find that out, okay, and then the aluminum contained in Al2O3 plus dissolved aluminum, if we add them up, that should be equal to the amount of the deoxidizer. Or putting the problem conversely, if you can find out, if you know the initial level of oxygen, okay, oxygen initial, and you tell me that what is the target or the final oxygen, what is your requirement, then I will be able to tell you exactly through material balance and chemical thermodynamic calculations that how much of aluminum you need to add. And there you must understand, now it becomes clear to you that this calculation is going to be totally disturbed if you have a FeO present in the slag phase, then the aluminum, because it is lighter, you have added it, it floats up, it gets exposed to a slag which contains iron oxide, and as a result of which what happens, aluminum rather than going into the melt, reacting with the melt, it is reacting with FeO, which is unaccounted for. I am accounting for only this part, that I have an initial oxygen content which is given to me 600 ppm. How do I know it? I know from tapping chemistry, okay? And then this is the target, which may be 20 ppm oxygen. So, I want to eliminate 580 ppm oxygen, and now I want to find out that. So, we can understand that if we have 500 ppm oxygen to be 580 ppm oxygen to be removed, okay, we can very well find out from the formula itself through stoichiometry that if 510 ppm oxygen is sitting as Al2O3, how much of Al2O3 we have generated, that can be very easily calculated, and how much of aluminum is there in that alumina generated, that also can be easily calculated. So, this much of oxygen where it has manifested, 580 ppm oxygen has manifested in the Al2O3, which has formed as a result of deoxidation. Okay? So, we can, looking at the formula, we can find out that how many grams of oxygen reacts with how many grams of aluminum, okay? And then we should be able to find out that 580 ppm of oxygen, and of course, I have to give you the ladle capacity, it is 30 ton ladle or 60 ton ladle, then you should be able to find out that how much of aluminum is sitting. So, all the oxygen removed is sitting in the Al2O3 generated as a result of deoxidation, and a part of the aluminum that you have added is sitting in Al2O3 in combined form, okay? And there is a second part, and that second part is this part that needs to be calculated, okay? So, this is the final, so this is the aluminum which is in equilibrium with 20 ppm oxygen. So, I have to now carry out that there is an equilibrium between dissolved oxygen, dissolved aluminum, and the Al2O3 which has formed. And if I assume that Al2O3 formed has is in pure phase and it has an activity is equal to 1, and that the final oxygen, target oxygen is given to me, and that K equilibrium value at 1600 degrees centigrade is known to me, I should be immediately able to calculate the Henryan activity of aluminum or the corresponding wet percentage of aluminum, which is remains in the dissolved. This aluminum was non-existent when we made steel in the primary steel making vessel, but now onwards this aluminum is going to sit in steel, okay, till we deliver it to the customer. And therefore, it is very important for us that the deoxidizing element must not contaminate steel or must not violate the prescribed composition. The deoxidation is to be carried out in such a way that the final stipulated composition does not get violated. This is a very important point, otherwise the customer is not going to accept our steel. Okay? So, therefore, we should be able to calculate aluminum, and then once we calculate the Henryan aluminum, we can convert it into wet percentage, and then we add these two components up, the aluminum tied up in alumina as well as the dissolved aluminum calculated from thermodynamic equilibrium at the given temperature, sum the two up, and that is what is your total aluminum requirement for the process. So, if you want to do deoxidation, okay, by aluminum, you can a priori determine that how much of aluminum needs to be added in order to fulfill, and of course, there could be, as I have indicated, 0.1% FeO, there could be some loss. Okay, so you can add plus minus 5% or a little bit more than what is. So, the whatever you are calculating is an ideal calculation. So, there may be losses. So, you can just back it up with additional 5% and then add the deoxidizer element into steel, only ensure that there is good amount of mixing, rapid dissolution, rapid melting and rapid dissolution, and such that the reaction can really take place. When you have manganese silicate, for example, ferromanganese silicate or silicomanganese, which is added, which forms silicomanganese. Now, in this case, what happens is, because we will require deoxidation calculation now, the activity of silica and activity of MnO is not going to be one. In this case, when you have calculated, the same calculation is to be carried out. For example, if I say that I have removed from 600 to 300 ppm, 300 ppm of oxygen, delta O is equal to 300 ppm is removed. So, we know that all this oxygen are sitting either as MnO or as SiO2. So, therefore, and these are sitting in, if I know the formulae which I have MnO. So, in 2:1 proportion, as you can see here from this particular formulae. So, therefore, the same calculation is to be carried out to find how much of manganese is there. If I write down the equilibrium, so you will have HMN, so you have to calculate HMN, you have to calculate HSI. But the calculation of HMN and HSI is not going to be straightforward, because of the simple fact that now, because silica and MnO are in combined state, their activity as opposed to the activity of Al2O3, which I have taken to be unity in the case of calculating the total aluminum requirement, I cannot substitute an unit activity. So, I have to use the correct activity of SiO2, correct activity of MnO, and of how do I know this? I require in such case an activity composition diagram. So, I will look at the phase diagram between what? Phase diagram between MnO, SiO2, and this is activity composition diagram, where activity will be given in terms of composition of the various species. So, if I know the composition, MnO SiO2 composition, in that case that composition can be found out easily by performing chemical analysis, and then we can say that we go to the activity composition for this binary system MnO SiO2, that corresponding to that composition, if it is 55% SiO2, 45% MnO, what are the activities of SiO2 and MnO, then I should be able to calculate HSI easily, HMN also easily, and then I should be able to calculate MnO SiO2, the deoxidation product which is formed. I should be able to calculate the weight percent of manganese which has gone into steel. I will be able to calculate Si. So, the assumption of an unit activity or pure deoxidation product in the case of Al2O3 gives us an opportunity that such a activity composition diagram is not needed, because always pure deoxidation product is being considered and the activity of the deoxidation product is taken to be equal to 1. So, whenever you will be doing the deoxidizer requirement for complex deoxidation cases, you have to do all these calculations, but you will require an additional information, that is the corresponding activity composition diagram, and that will only allow you to perform the deoxidation calculation completely, and you will be able to know how much of silicomanganese is to be added and how much of aluminum needs to be added into the steel. If you, for example, you must understand also that there could be, for example, if you want to do a deoxidation with manganese silicate, ferrosilicon, and then after some time you may do the final deoxidation from 300 ppm to 100 ppm. So, the first stage reduction is through silicomanganese, and the final stage of stringent reduction is through aluminum addition. Then you add aluminum. In that case, what happens? More complex phases can form. Okay, so aluminum silicates can form, manganese aluminum silicates can form, and in that case, the deoxidation calculations can even become more tricky. Okay, and they will involve ternary, quaternary systems, and but simplistically, if you consider simple deoxidation vis-a-vis one complex deoxidation by silicomanganese, I think with a simple binary activity versus composition phase diagram, you should be able to perform all necessary calculations pertaining to deoxidation of steel, and then you can advocate that for a given to satisfy a given target, oxygen target, how much of deoxidizer you have to add into the bath. And as I said, that if there are some, after doing the deoxidation, if there is some problem that no, you have not been achieved the target deoxidation, then you can do that trim adjustment during subsequent stages, and that we will discuss when we talk about ladle metallurgy steel making process. So, the gross deoxidation can be carried during the furnace operation, and final target chemistry in terms of dissolved oxygen to the level of 90-95% confidence can be established during this stage, and subsequent adjustment of final oxygen can be taken care of during the LRF treatment. Now, let us look at that deoxidation. I have assumed that all this, because this rests on the calculation rests on the assumption of an equilibrium, and I would say that an equilibrium is going to be very likely in the context of deoxidation reactions, because temperature is high, so the rate of reactions are going to be very fast. Also the melting and dissolution is also going to be not slow, they are going to be very high because of the large driving force for temperature, heat as well as mass that I have already mentioned. So we could expect that the deoxidation reaction will proceed towards equilibrium quite fast, and there will not be much barrier to nucleation, particularly nucleation. There are so many kinds of solids, etc., walls, vessels walls, and nucleation, as you know, are heterogeneous nucleations mostly. So therefore we can expect that the deoxidation reactions will go to completion within a very short time following the addition. So the equilibrium between melt and the deoxidation product is going to be established. Whether the deoxidation product and the melt are simultaneously going to be in equilibrium with the slag or not, that is a different issue that we do not ask. But as far as deoxidation product and melt equilibrium is concerned, there is sufficient indication from the occurrence of the deoxidation process, given the rates of chemical reaction, given the rate of heat and mass transfer, that there is no nucleation barrier, that the assumption of equilibrium is not too bad. It will work, and it will give you therefore yield reasonable value of deoxidizers that you will calculate offline and apply in your plant practice. So as we have seen that the deoxidation product could be liquid and deoxidation product could be solid. These products, as they are nucleated everywhere in the system, can remain entrapped, okay, and they can remain in steel. For example, they have a rising velocity, they can rise, and the rise velocities you can compute, for example, with Stokes' law, which you can write something like g dp square, the particle diameter, into delta rho, where delta rho essentially represents the density differential between the deoxidation product and melt, okay, and dp is the particle size of the deoxidation product, and the smaller is this, the smaller is the rise velocity. So very small particles, therefore you can expect, if it forms here, which is 3 meters or 2 meters from the surface, these will have not a chance to float out really. We do not want deoxidation product to remain in steel. The deoxidation product, if it remains in steel, it contaminates steel, it impairs steel's mechanical properties. So our necessary requirement is that the deoxidation product should not be entrapped. Looked at from that point, because the deoxidation products will be floating in the system, I would prefer liquid deoxidation products then solid deoxidation products over solid, and that is why I have written it number 1 and this is number 2, because while they are floating, liquid can coalesce with each other, becomes bigger, and as the particle size becomes 2 times bigger, the terminal rise velocity becomes 4 times bigger, okay, and as a result of which they can float up. On the other hand, coalescence efficiency is efficiency of coagulation or efficiency of coalescence for solid particle is not so large, and as a result of which what happens, solid particle do not readily form bigger mass by coalescence, and as a result of which they tend to float relatively slowly because they are diameters. These are smaller diameter particles, these could be bigger diameter particles because of coalescence. So that is why they are desirable. That is why if you use 100% aluminum as deoxidizer, there is a good possibility that a lot of alumina particles may remain entrapped in steel. The entrapment of deoxidation product, okay, contribute to what is known as inclusions in steel. If steel is free from inclusions, we say steel is clean. So the cleanliness is a term which gives us an impression of how successful you have been to eliminate the deoxidation product from steel. So therefore, we will say that when manganese silicate is going to form, there is a liquid deoxidation product. Rarely we will find manganese silicate deoxidation products. Now, the inclusions, if you do a general size kind of a range, so removal efficiency and size range, size of inclusions, then you will see it approaches something like this, and this size is something around 100 microns, and this is about 100%, which essentially tells us that you will rarely get particles, inclusion particles more than, unless your process is really bad, you will not get something like 140 micron particle deoxidation products, because these particles, because their diameter is quite large. So, we are talking about micron size particles here, not millimeter size particles. Okay. So, 140 micron size particles, we have sufficiently large terminal rise velocity, and they will float up from the mid bath point, mid depth position to the free surface, or to be absorbed by the slag in about 5 minutes, 4 minutes or something like that. So, that is why we see that removal efficiency is nearly 100%. So, that is why we are desperate to get bigger particles. Okay. So, that is why we are desperate to get liquid, but this is not so efficient. So, if you use aluminum, then as we are desperate to get a liquid deoxidation product, their strategy in steel industry is that somehow by injecting something, can we convert this solid alumina into liquid or not, and that is the subject of calcium injection in steel that we will discuss in one of the lectures in later classes. So, we would like to have liquid deoxidation product, we would like to have less contamination or less entrapment of the deoxidation product in steel. So, and this cleanliness determines the mechanical properties of steel to a large extent. Okay. The performance, service life, the performance of steel are largely dependent on how, to what extent you have been able to produce clean steel or steel free of inclusions. If you have 10-20 micron particles, they are not of much problem. Okay. But if you have 40, 60 or 80, and the different customers have different requirements, because for example, in ball bearing steel that we have discussed in the context of electric arc furnace steel making, they say that it is not more than 20 micron size inclusions are available. For other applications, again 40 micron size, 50 micron size inclusions is fine, and it is mostly the efforts are made to remove steel inclusions from steel which are in the range of 40 to about 80-90 microns, and how to eliminate them is the real challenge in steel making, in our drive to produce clean steel. Cleaner is the steel, better is the service performance, better is the life of the steel, and better is its mechanical properties. So, from that perspective, we just not only have to deoxidize the steel, but we have to make sure that the deoxidation products do not remain entrapped in steel. And these inclusions which form out of deoxidation products are also called as endogenous inclusions. As opposed to endogenous inclusions, we can have an exogenous inclusions also, exogenous inclusions, and exogenous inclusions, for example, if you have a little refractory, okay, and this little refractory piece, okay, somehow say it is an 80 micron size piece which is worn out and which remains. How can I know that little refractories contain MgO? So, if I look under microscope, find out the composition of the inclusion and it contains MgO, then I will know I have not added Mg, magnesium, into steel. So, where from magnesium has come? It has come mostly from refractory. So, this refractory origin of the inclusions tells us that it is of exogenous origin. So, we can have inclusions in steel, endogenous and exogenous. Bigger exogenous inclusions in generally not problem, particularly where unless and until when good old days when we are students, possibly people used to get exogenous inclusions, but good steel making companies which uses very high quality refractories, etc., exogenous inclusions per se is not a big problem. It is the endogenous inclusions of the deoxidation products which are of more importance. We will continue with this.